Food chains are defined as linear networks that model the transfer of energy from organism to organism. A food chain is the building block of a complete food web. At the top of the food chain is the apex predator, in this case, the lion. A predator eats other animals, and an apex predator has no predators. In nature, lions eat deer. This is modeled as such: an arrow from the deer headed to the lion. Deer's diets mainly consist of grass, and so on and so forth. Our question is, how long can a food chain get? To answer this question, we need to employ random graphs. The concept of random graphs was first introduced in the 1959 paper titled On Random Graphs by Paul Erdos and Alfred Renier. Random graphs are represented using various models, but we'll now use their model, the Erdos-Renier model. It defines a random graph as a collection of vertices with edges that can each independently exist with a certain probability p. To further understand, let's zoom in. For example, the existence of a directed edge from the blue vertex to the red vertex can exist with probability p. We assume all probabilities are equal for all edges, and this is called the binomial random graph. Zooming out to our model, we can now represent our food chain by labeling our vertices as our species, and the edges now demonstrate a predator-prey relation. For our current graph, this is the longest food chain, or the longest path from an apex predator to a basal species. So the length of this chain is the graph's height. But what is the case when the number of species in this food web tend to infinity? We now want to know the height of this graph. Does it look like this? Or does it also tend to infinity? The answer to our question is in Cohen's theorem. Cohen's theorem states that for a food web graph G of order S and height m, there exists a positive integer m star such that, as S tends to infinity, the probability of m being m star, where m star plus 1 tends to 1. That is, the height of a food web graph approaches a positive integer as the number of species in the graph approaches infinity. We won't be going into too much detail concerning the proof, because as you can see, the proof is quite elementary. Basically, we first find m star, we use Stirling's approximation to bound the growth of m star, then we bound m, the height of the graph, between m star and m star plus 1. So, using Cohen's theorem on our food web representation, this means that as the number of species goes to infinity, the food web forms communities, each of which has a height less than or equal to m star. So the moral of the story is that even in food webs, you can only go so far.